get going. I'm Vidya Arvind. Want to talk about resilient Cassandra. How do we apply backpressure, and what do we use to apply the backpressure resource utilization and query metrics? And this is Will.
Yes, I'm William Shore. I work with Vidya on the key value team at Netflix.
Super. Let's get this going. You must have seen this picture. All the places that red is there, that's where Netflix is streaming. And we deploy our databases in 4 regions, and we replicate everywhere. This is abstraction layer for us, where our databases has an abstraction layer on top, because client application connects to abstraction layer, and abstraction layer redirects the traffic to our databases. And database looks like something like this. You can see some pictures there about CPU and disk utilization metrics. When there's a lot of traffic, you see CPU utilization being high. Disk, when it gets hot, we see a trouble state of Cassandra. CPU also is struggling. When that happens, how do you protect your database is all we are going to talk about. We can, the animations are gone, but once we want to protect the database, there's a few ways to protect the database. We can scale up to many nodes. That way, when the traffic comes in, we can protect our databases. But when there's more traffic coming in, then we are still in a trouble state. We can also scale up by using more buffers. So in a stateful system, you use a certain amount of headroom in your servers, but when you're dealing with Cassandra nodes, you might have to also think about your background processes like compaction, repairs, and things like that, adding more headroom to Cassandra nodes and protecting our Cassandra servers. That's what we call as a background buffer. And there is also an instance headroom that you usually maintain for stateful and stateless systems. That's all great, but what if more traffic comes in, even after some amount of headroom you added, even after you scale to pre-scale the cluster to number of nodes, you are in a hotspot where the traffic cannot be handled by the cluster and you can't scale fast enough. There are few techniques that Netflix applies for backpressure techniques and traffic surge techniques. And those are traffic shifting, where you shift the load from one region to completely other regions. Traffic steering, where you take the latency metrics and say, okay, where can this latency be handled across our regions, and just move the traffic to those, steer the traffic to those regions. That's all great, but the database is still underneath replicating the data and still in a trouble state. So we can throttle the data by applying some concurrency limiters. Prioritized load shedding is another interesting technique that we'll cover later. Prioritized load shedding, request load shedding, and queuing is another technique that you can do as well. Queue the data, add latencies. That way, latencies becomes where you throttle as well. These are some of the techniques, but we want to dwell deep into how we are handling the surges, traffic surges, using load shedding, and specifically prioritized load shedding. And Will take over.
Thanks, Vidya. Yeah, so load shedding is our newest approach for handling exactly this kind of case. When traffic surges above the capacity we have, what can we do to handle it? And our answer is we can shed the load. We can decide this load we're not able to handle, we're going to just reject this request right away. But this approach kind of obviously has some risk to it, some downside to it. You're going to have impact by the very nature of what you're doing on the downstream service. So you have to make sure you're doing this in a principled way. And the way we are thinking about this is you want to try to make sure you're doing no harm to the use case. So you need to ensure that the shedding you do leaves you in a net positive state, so that you shed some traffic and the rest of the traffic gets that much better, that you have done this than just doing nothing at all. Otherwise, you really are just harming your own availability, your own resiliency. So the way we aim to do this is by metric-driven shedding. So we kind of have our architecture here again, and we have these protos. So this is the information that we're propagating down the stream. So the Cassandra nodes are able to propagate this system utilization proto, where they can tell the abstraction the compute utilization that they're observing and the storage utilization that they're observing. And we're using virtual tables, Cassandra virtual tables, to propagate this through. And we've added some customization into our Cassandra client to kind of pull these virtual tables in a safe way and keep kind of the right amount of caching there. So as not to overwhelm the database when trying to observe these properties about it. And we can talk a little bit more about that later as well. And then we have this service utilization, which can represent both the utilization of the Cassandra database, but then also some more information, maybe information about latency, maybe information about other data stores or that you're writing to from your abstraction. And so we kind of summarize this whole thing and push that back to the app. And then the app themselves, if they are interested in doing so, can make informed decisions, apply back pressure, drive their queue at some slower rate. So we making this information available empowers our clients to make those kind of decisions. But even though that's available, we still need to protect ourselves. We still need to shed load when things get bad. So I'll focus on that. I'll talk about system utilization and specifically what we're measuring. So first, talking about compute. Measuring compute is difficult. A lot of the signals are noisy. You don't want to shed load too early. You don't want to shed load when you don't have to. And one of the obvious candidates for measuring the kind of compute utilization is the CPU utilization itself. But we found this to be a noisy signal. It's a noisy signal for a couple of reasons. The first is it's not actually necessarily something that you want to shed on when it gets high. In fact, in some sense, CPU utilization is something you want to maximize. It's a measure of efficiency. It's a measure of how much time you're spending, or rather your cores are spending idle. And so you don't want idle cores. And so it doesn't make a lot of sense to say, okay, at 50% CPU, I'm going to start shedding requests. So, and that's actually exactly the other reasons. It's hard to pick a number. So instead, we've turned to PSI metrics, which are metrics that are available in the Linux kernel. It stands for pressure stall indicator. And these are a measure of queuing. And specifically, they measure how much time over some given interval tasks spend waiting to be scheduled in the run queue, waiting for a CPU. So the task is ready to go, but there just is not enough resources to actually execute that task. And that is really what you want to measure. That is a measure of, we have these tasks ready to go, we have this work we want to do, but we don't have the resources to do it. And so we've found this to be a much more reliable metric here. And you can kind of, this graphic shows the CPU utilization can shoot up, especially if you have very evenly spaced traffic, kind of in a queue driving or load testing scenario. And you can push your CPU utilization very high, but your queuing remains low. And that disambiguating that case from the case when you're actually under pressure is the kind of key insight of PSI. The final thing I'll mention is that it's still hard to pick an absolute number to shed on with PSI metrics, but you can kind of work around this by normalizing your PSI by the amount of queries you're doing. And this gets you to a number that's fundamentally something like, how much time per request am I spending purely on queuing that I wouldn't be spending if I had more resources available to run these tasks as they came in. So that's compute. I'll move on to disk. Compute is kind of the obvious example of what you want to shed on, but disk is equally important. I think in the last talk, we don't have this on the slide, but someone said that like disks filling up on Cassandra is a personal version of hell or something. I think that we should have put that on the slide because it's absolutely true. When disks fill up, not only do you see like significant CPU pressure, you can see slowness in many cases, but operations become fundamentally much more difficult. You have to move much more data around, and the more they fill up, the less time you have to do it. It's this kind of really tough situation. So monitoring storage and pushing back on the writer when storage is filling up is important. One thing we realized in doing this is that Cassandra has a built-in way to check the disk utilization, and this is a very accurate measure of disk utilization. It walks the whole file tree underneath the Cassandra directories. It also looks at the mem tables. It's very advanced, it's actually too advanced for our use case. We don't need that level of accuracy. And in fact, especially with newer versions of Java, where there's not a cache of the file system available in the JVM due to some changes in the consistency guarantees, this is very heavy. So running this even a few times a second, if you have a lot of nodes, ended up using a lot of CPU. So instead, we are using a very simple approach to getting disk utilization here, but which looks at the entire node. It actually is desirable as well, because even if something else is filling up your disk, you want to know about that too. So that's disk. Finally, I'll talk about request priority. We mentioned that this is prioritized load shedding, not just normal load shedding. That's because we have alongside here developed a system to propagate the priority of a request from the client app up to the database layer, so that when we do make a shedding decision, we can make it in the context of the importance of each request. So we can say 2 requests come in and the use case can tell us, well, this request is just a backfill, this is some bulk traffic, but this other request is really critical. Like if this fails, there will be user impact. And we can use that information as the system resources work their way up. We can make decisions per request based on the priority of that request. So here, this graphic shows a bulk load being shed as we reached some limits here, but the critical traffic remains resilient. So finally, I'll talk about what's next. We started with PSI metrics for compute, but they are also available for memory and I/O. These are much less frequently our bottlenecks, but they absolutely can be for certain use cases. And this is an additional form of utilization metric we can push back. We can use the same kind of system to implement quotas and get kind of quality of service guarantees at a logical layer. So we can have multiple kind of logical use cases, multiple namespaces as we call them, using the same infrastructure. And we can help shard the underlying infrastructure and the underlying resources across those logical layers. And finally, we can do token-aware load shedding. So one limitation we see right now is that if you have a hot partition where a couple nodes in your cluster get hot, this can drive the averages up sufficiently that you load shed too early. But this is actually a solvable problem. We can push this information down in a token-aware way so that we can make decisions on which load to shed based on the partition that data will hit, that query will hit. And this actually is important for our do no harm principle. Right now, you could potentially have a hot partition and start shedding load in partitions that aren't hot. And there's really no reason to do that. That's a net negative on your system. So this is a follow-up that we want to make. Yeah, I think overall, this is a project that's been really good for our resilience. And I think it uses a lot of kind of Netflix-specific infrastructure, but there's a lot of opportunity to take this stuff, build it into Cassandra, keep thinking about and iterating on the way we do this, and push this kind of work up one layer out of our abstractions and into the database itself. So I think we're excited to pursue that as we go. I think that's it for us. Any questions?
You open source it already.
Say it again.
You open source it already.
We have not, but yeah, I think it's something we are interested in pursuing.
From what I understood from your last comment, you were doing the shedding not at the Cassandra layer, but your layer in front of Cassandra.
That's right. We shed at the abstraction layer itself. Cassandra is responsible only for telling us when it's in trouble, when it needs us to shed, and then we use our abstraction to do the shedding.
Do you have any preference on what kind of load you shed? Like, do you only shed the heavy hitters, or once that limit is reached, you're shedding all load?
So if I go back to this slide, so within the yellow, basically we divide our, say compute ranges from 0 to 100, some number. Within this, the green range will shed nothing. Within the yellow range, we'll make prioritized decisions, but we don't make them in the sense of heavy hitters versus lightweight traffic. We make them based only on criticality. So this is something we have looked at, like shedding heavy requests is potentially another approach, but we've taken the approach instead of saying, we want this to be use case specific, we'll shed requests that you tell us are unimportant. And that for at least for our use cases, that tends to work well. And then in the red zone, as you alluded to, we shed everything. We say, your disk is nearly full, no more writes of any sort.
Sure. So follow up to that. So you already have all the knowledge on the Cassandra server side. What is the reason for not doing the load shedding on the server and passing it to this consumability to the client?
So
So-
we need to, sorry, that decision has to be made in our sidecar or other processes. We don't, that's a long run process. We run abstractions, which exactly does that. That's why abstraction is built, and we can build a capability that that is agnostic of our database as well. So that's the main reason for us to build that capabilities. That's one, but Will also showed the picture where you send the data from Cassandra. Some metrics are sent to abstraction layer. Abstraction also sends some metrics back to the client. We want to shed earlier than later. So yeah, we might exhaust other things like TCP buffer and things like that. If we are in Cassandra trying to shed things, we want to catch what is a problem earlier on and start shedding really earlier on. The one client app that we put, that could be layers of client apps. And if we pass that information all the way to the source where it's generating the request, it's even more resource efficient as well, right? So those are some of the, you have anything?
No, that's exactly right.
So one of the last things you mentioned that in case of load shedding, like if the partition is hot, you shed the load to partition if it's not hot. Like how do you do that? Doesn't Cassandra use like consistent hashing and the partition values?
I'm sorry, can I interrupt
Please.
here? Because we need to stick to the timelines. Very interesting questions, very interesting talk. Let's continue to connect offline, right? And get that answer, right?
Thank you.
Yeah.
Thank you very
Thank
much.
you, Vidya.